This presentation is delivered by the Stanford Center for Professional Development.
I think we're on. Do you have any you can turn off all amplification in here. I don't know if you have any on. But let me start with some announcements. The first is this. For those of you who are currently asleep and viewing this at your leisure later, we know who you are. So let me repeat that attendance is a requirement of this class. So now that it's on, when we put it on SCPD, it doesn't mean you can sleep late. Of course, that doesn't apply to our people here. So, okay, all right. Couple of real announcements. Actually, that was a real announcement. Oh, the first one is we've assigned homework 2. We have no way of getting in touch with you because for some reason the registrar has not populated the course list yet. Or maybe that's not true today, but it was true yesterday. So homework 2 we've assigned, and these are gonna be pipelined. So we'll produce a homework whenever we feel like it. It'll be due roughly a week later or something like that. No matter when, they'll overlap and all that sort of stuff. So you'll be fetching homework 3 sort of while you're still processing homework 1 or 2 or something like that. I don't know. We'll see if we can get 3 deep. We might, actually. We'll see if we can do that. So homework 2 is actually assigned. Let's see, a couple of other announcements. 2 are important. One is that sometime this week, maybe even today, we're going to schedule what is going to play the role of a section. There will be no section where you go and the TAs review stuff and you ask about homework 2, problem 1. We won't even have that. What we will have in the section is once it's scheduled, and we're hoping it could be scheduled as early as this afternoon or who knows what. So please pay attention to email. Not that we have an email list to email you with, but assuming we did. The section, we're going to actually the first couple of sections are going to do nothing but cover sort of discussion of projects. So I'll lead a couple of those when I'm, if I'm around and can do it. And so that's, but you'll hear more about that on the website or via email if it ever gets set up. Now the other one is quite strange. In 364A, you might recall, we made, I believe we made SCPD history by taping ahead the first lecture, not only the quarter before, but the year before. So I think we're going to do it again. We're actually going to, we will schedule for this class what could well be the world's very first tape behind. So we're actually going to go back and redo lecture 1. Really, I'm not kidding. So that it can go on the web or something like that. Yes, it's strange, I know. So at some point, I will appeal. Maybe the right word is beg, grovel. I'll do something to get at least some of you statistically to show up to what I believe will be the world's first tape behind, where we'll go back and retape lecture 1. So, of course, I can't say all the controversial things I said then, but that's okay. That's the disadvantage. Okay. If there's no questions about last time, then I think we'll just jump in and start in on subgradient methods. So for subgradient methods, we looked at the subgradient method is embarrassingly simple, right? It's you make a step in the negative, in a negative. I'll call it the negative, but the correct English would be in a negative subgradient direction. The step size is not chosen, for example, by the methods you would use in a gradient method. In a gradient method, you're looking to minimize the function, and you might use a greedy method to minimize f, or just get enough descent in f, and that would be via a line, some kind of a backtracking line search or line search. Step size in subgradient method, totally different, and actually, frankly, bizarre. Here's what they are. They're often fixed ahead of time. That's the strangest part. So very often, it's something like this. It's just a constant, or it's a constant step length. or at some fixed sequence like 1 over k. And we'll see, in fact, that there's not really a whole lot more you can do with the subgradient method than this. That actually being smart in choosing your step sizes, generally speaking, I haven't found it to work that well. So, okay. So the assumptions are standard. By the way, if you look in various books, you will find proofs where the assumptions are much weaker. I make as many assumptions as I can to make proofs fit on one page, because I think if you can get that, then you can easily go back and read the 4-page version in the Russian book, written in English though. So and do that. So for example, in particular, you don't need this constraint here, this assumption that there's a global Lipschitz constant on f. That's not needed. That complicates the proof if you don't have it, but that's not I guess that's not our point. Okay. Okay. So let's jump in. Here are the convergence results. I think we looked at this last time. And then let's look at how the proof goes. So here's how it goes. It works like this. What is going to go down is the Euclidean distance to the optimal set, not the function value. So if you remember the proof of the gradient method, well, there's several things that you can use as a Lyapunov function in the gradient method. You could use the function value itself. So the function value goes down. And then, of course, you have to go, once you know something goes down, it's got to converge. The question then is whether it converges to the optimum. But that's a simpler thing to argue. The other option for a Lyapunov function, or merit function, or whatever you want to call it, whatever the function is that certifies progress, the other option in a gradient or Newton-like method would be the norm of the gradient. That's another possible Lyapunov method. Here, what is going to serve as the Lyapunov function or the merit function or whatever is actually the distance to the optimum. What was that? Oh, maybe that was this thing timing out. Okay, so I'll use the manual timeout prevention procedure. What's that? Yeah, that's all right. I'll fix it later. Okay, so the distance to optimum is what's going to go down. Now, actually, there's something quite interesting about this already, and I'll say this now because it's going to come up as we look at what happens with this subgradient method. Let me tell you what's weird about it. If you're running a gradient method or a Newton method or something like that, you know the function value. So you know if you're making progress because your last function value is -10. At your next step, it's -10.8, and you know you just made whatever 0.8 progress because the function value went down by 0.8. Here's the weird part. You don't know this. So although it is going to be what's going to be going down, you won't know it. So that's going to be what's a bit odd about it. Okay, so let's look at this. The argument goes like this. xk plus 1 is in fact precisely this. That is xk plus 1. And now I regroup xk minus x star, and I pull it, and I expand this. So I get the norm squared of the first term, I get the norm squared of the second term here, and I get twice the inner product, and that's here. Now, this inequality holds, in fact, that's literally what it means to be a subgradient. That's this inequality. Okay? So if you apply this recursively, this basically says that your distance at the next step to x squared is less than or equal to the old distance to the optimal. And then let me point out which terms are good and which are bad. This term is bad because this is an increase in distance to optimum. This term is good because this thing is bigger than that, well, by definition of f star. So therefore, that's positive. That's -2 alpha k. Alpha is positive. So this is the good part, and that's the bad part. Okay? So what this says is, unless this term overwhelms that term, you actually don't make progress on each step. But notice what it does say. It does say that when alpha gets small enough, you absolutely make progress towards x star, which you don't know, by the way. So that's what this says. So what happens is you simply say, well, look, if this is less than that, I simply apply recursively this inequality. I plug that here, and I end up summing these two terms. And what I'm going to get is this. I'll get this. If I apply this recursively, I get that the next state minus x star, that's an optimum point, is less than or equal to the initial deviation from x star, and that's going to be less than r squared. That's sort of our assumption here. Minus twice this sum here. That sum of these are positive numbers. Plus, and then there's this term over here. And so, of course, this is not a good term. That's the good term because it's well, actually, it's good. Everything works out quite well here. And now I'll make some. I'll do some things here. Let's see. This hasn't changed, but here I'm just going to replace these with their maximum value, which is g. Okay. Now, by the way, if you have a function that's differentiable, as you approach optimum, what happens to the gradient? It goes to 0. So, I mean that has to happen. In fact, you can derive all sorts of bounds on that. That's maybe I should fix that. Or I'll, yeah. What's that? Oh yeah, you're right. That's actually what's happened. Hang on. We'll just power this guy up. It's panicking. Or it's not panicking. It's on the battery power save mode, so it's. Thank you. That'll. Because I thought I changed the thing. Okay. Let's see if it stays happy now. Okay. All right. So for a function that is differentiable, the gradient goes to 0. By the way, is that true for a subgradient method? If you minimize absolute value, what do the subgradients look like? Just minimize absolute value x. What are the subgradients of absolute value x? Well, they're mostly plus or minus 1. Right? So it is false that the subgradients go to 0. Right? They can remain big all the way to the end. And the subgradient method will be oscillating between, a small positive, small negative number. And the subgradients will always have magnitude 1. So that's the case. That's true for any minimax problem. The subgradients are not going to go to 0. They're going to stay large. Okay. Okay, so we get this. Now here we'll use a very crude bound that says that the sum, if I have a weighted sum, these are positive numbers. These are, I guess these are also non-negative. Well, I guess if there's, well, no, these are non-negative. One of them is actually equal. No, sorry, these are non-negative. And I'll simply replace this with the min of this and the sum. Now the min of this thing is fk best by definition, so you get that. And if I put this on the other side and divide by various things, I get this basic inequality. So everything's going to follow from this one inequality here. But you already see we're in very good shape. Because if you look at this inequality, here's what happens. This is the best thing you've found so far. By the way, this you know for sure, right? Because that you're keeping track of. Minus f star, and that's less than r squared. That's your original ignorance in, this is your original ignorance in distance. Plus g squared times the sum of the alphas divided by this. And you can see already you're in very, very good shape. Then there's a couple of ways we can do to make this work. But now you can see immediately why it would be that the sum of the alpha i's are going to have to go to 0 in these things. So that's the first, sum of the alpha i's, sorry, are going to have to be go to infinity. So that's going to make this thing diverge. Okay. So if you have a constant step size, that's just a fixed alpha. You plug that in and you get this. And if you take a look at that, you'll see immediately that as k goes to infinity, you end up with g squared alpha squared over 2 alpha, which is the same as g squared alpha over 2. So that proves that as if you just have a constant fixed size, well, people call it constant step size. It's not really the size. If you make a constant alpha, what happens is this. You will converge to within g squared alpha over 2 as k goes to infinity. So you don't converge, but you will converge to within some boundable distance from optimum. That's constant step size. Now, constant step length says you simply, and by the way, this is the classical subgradient method from, this is what you learn in 1971 in Moscow, is this one right here. So. Or with, actually, it's this with decaying terms here, where these are gamma k's. But that's the one you learn. That's the one, by the way, that does not need the Lipschitz constant, g, assumption. But not that it matters. But, okay. In this case, you get this. You get the best f minus f star is less than or equal to r squared plus, and then you get the sum of these things over here. And what we do here, went back two inequalities. You write it this way, r squared plus gamma squared k. And what happens now when you let k go to infinity is that this converges to within capital G gamma over 2 instead of g squared. So you get a slightly better bound or something like that. I'll say a bit about how the subgradient method works in practice. And in fact, you'll see a fair amount in the next week about how it works in practice. In fact, I guess you'll code up some and try this yourself. So, okay. So if we start with the canonical one is you have square summable but not summable coefficients or step sizes. And the canonical one is something like 1 over k. That's your classical sequence here. That diverges. It's not summable, but it's square summable. In this case, it's extremely simple because as k goes to infinity, this converges to a number. So that just converges to a number, which is the sum to infinity. And this converges to infinity, so obviously that goes to 0. Okay? So there you go. By the way, this is, since you've seen a whole proof, I want to emphasize how ridiculous this whole thing is. You've just seen an algorithm that is one line at best. You could make it 2 or 3 if you added some comments. Okay? It's basically, it calls a get subgradient method on a function, on a convex function, and it gets a subgradient. And it's basically x. Well, in fact, the algorithm is this. It's embarrassing. It's x minus equals get subgrad f dot get subgrad divided by k or something like that. That's it. I mean, it's a ridiculously simple algorithm. There's no line search, and it basically computes. It finds the minimum of any convex function, differentiable or not. Okay, so it's really it's worthwhile sitting to think about it for a minute, how ridiculous the whole thing is. So that's what it is. The proof, as you saw, stretches onto 2 slides, but that's expanding it out. It's really, we're talking a paragraph here with lots of discussion in there about the proof. So in other words, it's really quite trivial. Now we're going to find out. It's got some good properties and bad. I mean, as I'm sure you've already guessed by now, it's going to be way slow, but that's okay. Well, it's going to have some other virtues. But simply the idea that there should be a universal algorithm for convex optimization that's one line. The proof is barely 1 paragraph. I still find quite implausible. I mean, the whole thing seems ridiculous, and yet it's quite true. So, okay, stopping criterion. Okay, now if you wait until this thing, remember this is a bound on fk best minus f star. So now let's leave alone the fact that you really aren't going to know r, probably. Of course, you can put an upper bound on r there. That's fine. Well, that's not true. You might have some very crude bound on r. Sometimes you can estimate a g, but often not. Right? So this stopping criterion is a little bit fishy. In any case, waiting for this thing to be less than epsilon is really, really, really slow. It's also often not. I mean, it's just very, very slow. Now you can ask all sorts of questions. By the way, you should be reading the notes on this because there's a fair amount more in the notes than in the slides where things are discussed in greater detail. So you should be reading those. You could ask all sorts of cool questions, like you could take this bound here, and you could ask yourself, what are the choice of alpha I that minimize this? Now, think about what that would mean. It would mean what are the optimal step sizes? You fix a number of steps, and you want to minimize the upper bound on fk best minus f star. That's right. That's what you would do if you want to minimize this. Now, let's actually talk about that briefly. So we want to minimize this function here over choice of alpha. There's k alphas, right? So let's take a look at that. First of all, what kind of function of alpha is this, provided they're all positive? It's what?
Quasi-convex.
Oh, I agree it's quasi-convex, but I think it's more. Hint. It's a word that appears in the title of this course. What kind of function is this? Well, it's convex, obviously, right? Now, actually, why is it convex, actually? Somebody...
It's quadratic over
Yeah, it's quadratic over linear. It's a quadratic over linear function, and the linear part is positive, so we're totally cool. It's a convex function. Okay, so actually, that's very interesting. It means that choosing the optimal sequence of step lengths in the subgradient method to minimize the upper bound on fk best minus f star is itself a convex problem. Now, the question is, what's the solution? And I'll just mention this. It has to do with symmetry. If this function here is symmetric, in other words, if I apply any permutation to the alphas, it does not change the value of this function. Everybody agree with that? So that's clear because you just sum alpha squared or sum alpha I, that's all. So it is symmetric. Now, that means that if you what I'm going to argue now is that the alphas are constant. The optimal alpha is constant. Okay? And this is a general fact about the optimum of a symmetric convex function can be assumed to be constant. Well, constant. Constant means constant under the symmetry group. Okay? So, and let's see, the argument would go something like this. Suppose you come up with some set of alphas that's optimal. So you come up with, but they're weird. I mean, they grow, they shrink, they grow. It doesn't matter what they do. They're non-constant. Okay? And they're optimal for this. Okay? Well then, if I apply a permutation, that's got to be optimal too, because it's got the same function value, which you allege to be optimal. So if I take your alphas, which can vary, and I permute it any way I like, I get something that's optimal, because it has the same function value. Okay, now do this. Take all permutations of the alphas, add them up, and divide by n factorial. Sorry, k factorial. Okay, so you average over the entire symmetry group, the orbit over the whole symmetry group. Okay, you know what you're going to get? It's got to be optimal, and that's by Jensen's inequality, because I'm taking an average of things. This function, evaluated on the average, has to be less than or equal to the average of the function, but the function is optimal every time, so therefore it's optimal too. But when you average over all permutations, you get a constant. Okay? So that's my proof, complete proof, that in fact the optimal alpha here, sequence, vector of alphas is constant. Once you know it's constant, this is really stupid. You just remove the I here and put k in here, and you optimize, and you get this. So it's constant. And you get r over g divided by square root k. That's your optimum step size. By the way, you will see this come up in various things. It comes up in the lore also of, so it's ingrained in the history of the subgradient method. You'll see square root k's all over the place. By the way, is that square summable? Is it square summable? No, of course not, because you square it, you get 1 over k's, and those grow like log. So it's not square summable. On the other hand, this is what you would do to get the best bound after k steps. Okay, let's see. So the number of steps required, if I plug this into here, is this. And it's actually a quite beautiful number, Rg over epsilon. I mean, I think we can interpret it perfectly. If you go back to the initial point, so the initial point, before you've optimized anything, all you have is prior data. So here's what you have. You have an initial point x1, and you don't know anything. You haven't even evaluated one subgradient. The only thing you know is this. Someone has told you that you are no more than a distance capital R from optimum. That's what you've been told. You've also been told that the Lipschitz constant on your function is capital G. Based on that information, you can bound how suboptimal you are right now. Because the farthest you could be, the optimum point could be away from you is R, and the Lipschitz constant is G. So Rg, this is actually, that is basically your initial ignorance in optimal value. Everyone, if you were not allowed to do anything, this is an upper bound, probably a terrible one, but nevertheless an upper bound on f of x1 minus f star. Everybody cool on that? So this is your initial ignorance in f star. Epsilon, of course, is your final ignorance in x star. So this is your ratio. This here is the factor by which your ignorance improves over the algorithm. It's literally, I mean, if f is in dollars or euros or whatever, or something like that, it's a cost. This is literally the ratio of your actually, this is your prior to your posterior ignorance. And it says that the complexity is going to go like the square of that. Okay? So that's I mean, in other words, everything's interpretable here very, very, very nicely. So, okay. Now, I'll tell you the truth. It is cool because the proofs are so short to look at the proofs and things like that. And actually, good things have come from the proofs and things like that, like an understanding of what these step lengths mean and all that sort of stuff. But the real truth is this. When you actually use a subgradient method, and we will see applications, actually we'll get into stuff later today where you'll start seeing applications of it. And then over the next several weeks you'll see serious applications of it. Actually, it's going to come up in areas like distributed optimization. Look, it's so slow, it has to have its positive qualities or we wouldn't be here. So anyway, we'll see what they are. Okay, but here's the truth. The truth is there really isn't a good stopping criterion for the subgradient method. That's the truth. Unless there's something else in your problem. I think at one point, I know someone over that way asked about cleverness in finding a subgradient. If you have just a separate method to calculate a small subgradient or whatever, you might get lucky or something like that. But the truth is, in general, there's no good way to know when to stop in the subgradient method. And this bound, all the theoretical bounds are like way not too useful and so on. Okay, so let's look at an example. So here's an example. It's piecewise linear minimization. So you want to minimize this function. Now I should add, here's how we would do this. I mean, everyone here, you would do it, I mean, this you would do by, obviously you'd do this by, this would be very simple. You would do this with, you'd convert it to an LP and solve it. And nothing could beat that. Absolutely nothing could beat the efficiency of that. No matter which method you choose to solve the LP, wouldn't make any difference. That absolutely couldn't be beat. So it's to be understood here that this is not a recommendation or endorsement of this method for piecewise linear minimization. So, okay. So to find a subgradient for this max is very simple. You evaluate all these functions. You gather the function values. And then you find out, you pick any one of them which is at the maximum. Okay? So you just pick one that's at the maximum. If there's only one, no problem. You just pick that one. And we'll pick that j, and we'll take g as aj because it's the gradient of the one that is that's tight at the optimum. And the subgradient method looks like that. So again, it's just embarrassingly short method. And let's see how that works. So here's a problem instance with maybe 20 variables. It's a piecewise linear function with 100 terms, so it's the maximum 100 affine functions in R20. And it turns out for that instance, f star is about 1.1. I should add that all of the code for all of this, I believe almost all of it, I think maybe all of it, is on the website. So on the website, there's the lecture slides. There's also a tiny little link for notes. You should read those. Those are the more detailed notes. And then after that, it should be all the source code for everything. So if you want to see what we did. Okay, so here's f minus f star. Not an impressive scale. That's not 10 to the 0 and 10 to the minus 8, as it would be if we were looking at an interior point method or something like that. That's 10 to the 0, and that's 10 to the minus 1. So the bottom of this thing is basically 10% optimality. Okay, so this is constant step size with various step sizes like this. And here it is on a bigger scale. Note the number of iterations here. And it's doing something according to theory. This is something like, that's 10% and that's 1%. And actually some of these are not at all bad. For example, this method right here, and we do have to be a bit fair here. Because in fact, all we're doing, each step, the computational complexities, we have to evaluate all those affine functions. Okay? That's actually order nm, right? Because you multiply an nm matrix by a vector. That's all you have to do. It's m by n. So the cost, each iteration here is order mn. There's then, of course, there's a log m step where you calculate the maximum. but that doesn't count. And then there's a little order n step. Mn is what you multiply with here. Now, if you do an interior point method, what's the complexity of this? What if you use an LP to solve this problem? In fact, what's the complexity? Total, actually. What is it? You want to hear the mnemonic for this? The mnemonic is this. If you know what you're doing, it's always the big dimension times the small dimension squared. That's if you know what you're doing. If you don't, it's the big dimension squared times the small dimension. Okay? So you want to do least squared, because basically, look, each step in this, you have to form something like, let's see, A is like that. So you're going to form A transpose DA. And that's what you're going to have. You're going to have to form that Hessian and then solve it. Actually, forming the Hessian is going to be the one that's going to cost you the most. And that's going to be order mn squared here. So compared to order mn, it means we're off by about 20. Now, this is very rough. It's disturbing to me that you're looking at me like that. So I know we went fast in 364A, but this is the time for you to go back and read it and figure these things out. So basically, and that's what comes from looking at these things too. You all coded this, so don't look at me. Like you've done this. So anyway, it really is, trust me, it's a least squares or a normal equation solve. In fact, forming A transpose DA is the dominant, is actually the dominant computational effort. And that's, if you know what you're doing, it's mn squared. So you're off by about n. And that means that in these things here, you really should divide by 20, minimum, to get it. And then these things aren't so bad. That's, well, they're not so good either. So you divide by 20, what do you get, 60? Okay, so on the other hand, an interior point method, by this effort, and we're being very rough here, by this amount of effort, 60 steps, it's way over. I mean, you've got accuracy to whatever, 10 to the minus 12 at that. You're done. You're double precision stationary after 60 interior point steps, right? So the point is these are slow. What's interesting is this one actually is a little bit attractive. It's almost attractive if what you wanted was something that's like 5% accuracy or something like that. But okay, this is, so anyway, bottom line is that shouldn't, it's not fair. I mean, you have to, don't compare this to the 30 over here you'd see for an interior point method, but this is more like 60 or something like that. So, okay. This is what it looks like for various other rules. The first one is 0.1 over square root k. And the other one is the square summable rule, just 1 over k. And that gives you these. Now, actually, there is something to note about this. And in fact, it's probably a very good thing to know about subgradient method. And this holds for gradient methods as well. For a little while, you do well. In other words, you do pretty well after a couple of steps. You get some serious reduction, and then it just jams. Now, the theory says that this is going to go to this is going to just go to 0, right? So, but it's going to go really slowly. In fact, if you read the notes, you'll see that these methods can't go any faster than 1 over square root k. That's very slow. So, if you're looking for high accuracy and you can avoid a subgradient method, that would be a really, really good idea. So, okay. Now, this is not bad, right? That's 1%. That's 10%. That's a couple of percent here. And in fact, for a whole lot of applications, a couple of percent is just fine. Okay. Now we're going to look at what happens if you know the optimal f star. Now, when you first look at this, you think, well, sorry, that's a bit circular. When you minimize it, how on earth would you know what the optimal value is? Well, we'll see actually, it seems ridiculous, but there's plenty of applications and cases, you'll see them in a minute, where you actually know the optimal value. I mean, often the optimal value is like 0, basically, and you know it's 0. And what you just want to do is find a point where f of x is near 0 or near 0. Okay, so, but when you first hear this, it seems quite absurd. And the optimal choice, and this is something due to Polyak, although, well, I talked to him about it, and he said, oh, no, everybody knows that. So who knows who it's due to? He would tell us. Okay, So, and the motivation behind this step length is this. And I'll draw a picture to show what it really means. The motivation is this. This is the inequality we used at each step. And it's simply, let's do something greedy and take the right-hand side and minimize it over alpha k. If you minimize this right-hand side, you get that. Now, of course, in many cases, that's totally useless because, of course, you don't know what f star is. But if you happen to know what f star is, minimizing the right-hand side here is, I mean, it's a reasonable task. Let me show you what it's based on. It's based on the following idea, if you wanted to get a picture for what this would be. It basically says the following. You're minimizing a function. Now, I've drawn it differentiable. And you're here. I'll draw it differentiable, but that's OK. And you know f star. Don't ask me why, but for some reason you know f star. And this step length basically calculates the point here. It calculates that point there. So what it does is it simply extrapolates the function affinely, or I guess most people would say linearly, finds out when it hits this optimal value, which has been conveniently supplied to you, and then that takes a step length that does that. Okay? So that's the picture. Oh, let me ask you a question. If a function is piecewise linear, how well, let's talk about how good this, well, let's slow down. This step size, now that you have the picture in your head, how does it work for quadratics? I mean, how does it work for I just drew it. So how does it work? How does it work for, just do it in your head. Just take a quadratic, take a point, draw the tangent. Okay, so how does it work? How fast does it converge for quadratic? What? Well, you make about half. I mean, I'm just talking about x squared. I'm talking about how do you minimize x squared using the Polyak step length. The answer is you kind of make about half. X gets divided by 2 each step, right? Roughly. So you're converging. It's pretty good. Oh, by the way, you can easily figure out ways to make this method work very poorly. You need a function that's very steep. So if a function is very steep, this is going to be really, and then is really steep, and then has a kink, and then goes down slowly. Until you hit that slow part, it's going to take you zillions of steps. Everybody see that? Because you're just going down, you're going very slow. Okay. How about piecewise linear? Is this a good idea for piecewise linear? How does this work for absolute value, by the way? One step. How about piecewise linear in multiple dimensions? What do you think happens? Yeah, okay. Yeah, it depends on the number of pieces. But actually, what happens for piecewise linear, this algorithm terminates finitely. Okay, it takes a finite number of steps. Because once you get, if you go in on a piecewise linear function and you look way down at the bottom where everything comes together, at that point, once you're on one of those faces, next step it's all over. Right? So this method for piecewise linear actually works well. So this is a step length rule that's kind of appropriate for non-differentiable functions. It's actually not that appropriate for differentiable ones. Okay. Now when you plug in this optimal step size, here's what you get. When you plug in the optimal step size, what's great is that for now, the distance to optimal actually goes down every step. So this is negative. In the subgradient method, it need not. All you can say is that eventually it goes down. And in fact, is you don't even know when it starts going down. You don't know x star, you don't know that, and so on. Okay? Okay, so in this case, your distance actually goes down every step, and by an amount, I mean, it's fantastic, and you can see immediately everything's going to work out in your favor. What happens is this. This thing goes down by an amount that depends on how suboptimal you are. Therefore, if you're suboptimal, if you're quite suboptimal, the distance goes down a lot. I mean, this is kind of just what you want. If it doesn't go down much, that's because you're nearly optimal. So it's perfect. Okay, now if you just apply this recursively, you get this. And what you get here is this. I can replace this with g, and then put g squared over there, and I get that. So this is the sum of the suboptimalities squared is less than r squared g squared. By the way, that's a faster convergence than the 1 over k. 1 over square root k, or whatever. It basically says the convergence is L2, right? That the suboptimality goes down and is square summable. right? So, for example, well, anyway, it can't be as slow as 1 over square root k or something like that. Now, of course, that's because you know f star here. So that's how this works. So here's the same piecewise linear example. Now, of course, in the piecewise linear example, there'd be no reason that one would know f star. That's ridiculous, right? So you wouldn't know f star. So this is unfair. This is just to see what advantage would you get. And I think this is the Polyak, the so-called optimal step size is this thing. And you can see it does as well as the as any subgradient method is gonna do. And that's what this one is. Again, it's not terrible. That's what it is. Okay. So now we're going to apply this to a very famous problem. It's the problem of finding a point in the intersection of convex sets. So it goes way back, the problem. It's used in lots and lots of fields. And the method we're going to talk about, well, it's not going to talk about it. It's going to pop right out of subgradient method, is very classical. And it's used actually to this day in lots of fields. In fact, in lots of fields, they haven't grown out of it. Someone discovered it in the 60s, and they just never went farther. They just arrested development at this method. So I'll name some of those fields later, maybe. Okay, so here's what we want to do. We have a bunch of convex sets. They intersect. And what I want to do is actually find a point in C by minimizing the maximum distance to all of them. Okay, now this is a convex function here. It's a convex function. Oh, and if I minimize, oh, by the way, what's f star? What's the minimum of f? 0. Good. So this is a case where you know f star. And it's 0 because this is non-empty. So there's an x in all of them. There's an x that satisfies, all of these are 0. So f is 0. Max of distances don't get smaller than 0. So there's not, f star is 0. Okay? And we're going to minimize f using subgradient method. Now, how do you calculate a subgradient of the max of distances to a bunch of convex sets? Well, the way you do it is this. You evaluate all of these. So you evaluate all of these. You figure out you choose one that is maximum. Doesn't have, if there's tie, you break it arbitrarily. Makes no difference. That's the subgradient method. So you break it arbitrarily, pick one that's maximum called J, and then actually the distance to a convex set, in fact, if it's provided it's positive, is differentiable, always. Let me think about that. That's true. It's differentiable. Let's see, yes, that's true. If it's Euclidean distance, it's going to be differentiable. So, and the gradient is very simple. It's actually a unit vector that points from where you are. Well, let's see. Let me see if I can explain it. Here's you. Here's the convex set. You calculate the projection of that point on the convex set, and then the gradient points exactly in the opposite direction and has unit length. It's kind of obvious. It says basically to move away from a convex set at the highest rapid, as fast as possible, you should calculate first the point on the set closest to you. You should turn exactly around and go in the other direction. And if you ask how far, if you go 3 millimeters that way, how much farther are you from the set? The answer is 3 millimeters locally, right? So that's, I mean, you could also do this just by calculus or whatever, but the point is that's the gradient. So it's a unit vector. Okay. Now we're going to use Polyak's step length. So we just simply update like this. And let's see. Oh, here's what we do. So this is at the f minus f star and so on like that. And I simply get this. It's in fact, if you work it out, it's quite. It just works out perfectly. Everything works out. This is norm. It's the maximum distance, and that happens to be, if you pick J as the one that was farthest, it's norm. It's the dist. It's actually the norm. It's this expression here, which is the same as for the. It's the one for it's J here. So this is what that is. That cancels. This goes this minus that. That's gone, and the only thing you're left with is a projection. So it's that. So it's really dumb. So here's the algorithm. Ready? you have a bunch of convex sets. And let's see, so you have a bunch of convex sets. Let me just draw. I'll just draw the most famous pictures for 2, but it doesn't matter. I can draw it for, 3. Here's this, and then I have this. And the way it works is you're here, anywhere you are. Actually, you could never be there, but that's another story. So let me assume you're here. Let me assume, whatever, you start here. And what you do is you calculate the distance to each set. So that's the distance to the first one, that's the distance to the second, and that's the distance to the third. The largest one is this one. So you simply project the point onto this set. It's that stupid. I mean, really, it's that dumb. Then you're here, and now you calculate the distance to the 3 sets. Well, what's the distance to this set? 0, because you're already there. What's the distance to this set? 0. This set is positive, and so you'll go here, and actually, what happened? Did we do it? Yeah. Is that right? Yeah, I think so. In 2 steps, this one worked. This one converged in a finite number of steps. 2. Okay. But this is the picture. So by the way, this is called alternating projections because if there's 2 sets, it's extremely simple. You have 2 sets, you just project on one, then the other, then one, then the other, and you keep going back and forth. It always has to be the other one because after you've projected onto a set, your distance is 0. So if you want to know what's your maximum distance to the 2, it has to be the other guy. So that's alternating projections. Lots of variations on it too. So that's it. And our basic result says this, that our distance goes to 0 as k goes to infinity. In fact, we even have that sum of squares bound and all that. So, by the way, it can be quite slow, this method, and there's some very interesting acceleration methods for it. But this is it, very famous algorithm. So here's the picture for 2. It goes like this. You start here, and you project there, then there, then there, then there, and so on. That's x star. Now, in fact, the theorem does not say that you get convergence in a finite number of steps. What happens is you get your distance, that maximum goes down. That's what happens, and it goes down to 0. That's guaranteed. So basically, it says if you run it long enough, you're not very far from the farthest set. So that's what it says. There are variations on the alternating projections that will guarantee that you find a point in the intersection, provided the intersection is non-empty. And they'd be based on things like this, basically over-projecting. You back off each C slightly, you shrink each set slightly so that they still have intersection that's non-empty. Then you apply this algorithm to the shrunk things. And so and then what happens is our method says, the general theory says, subgradient method or alternating projections is your distance to the shrunk sets goes to 0, but that means after a finite number of steps, you're actually in the interior of the other steps. Okay, so what I just said was actually correct. It sounded informal, but it was actually correct. So, okay, so that's alternating projections. We'll look at an example, and then I'll mention some other examples. Let me just mention some examples. It's used in a lot of cases. So you're going to actually, so what you're going to want to do, and this is actually not a bad thing to do. Everyone should do this anyway, is you need to catalog in your mind the sets that you can easily project onto with low complexity. So actually, all educated people should know that anyway. So you just need to know that. Not just for algorithms, but for everything else. So let's actually talk about sets you can project onto. How about affine sets? Can you project onto an affine set? Yeah, sure. That's least squares. Come on. So you can project onto an affine set. That's easy. How about projecting, let's see. How about projecting onto a ball, a Euclidean ball? That's extremely easy, right? You wherever you are, you look at the center, and you go towards it, and when you hit the surface of the ball, you're there. Okay. Let's see. How about the non-negative orthant? How do you do it? Yeah, you just truncate all the negative numbers. Okay. Let's see. I can do a couple of others. What would be some other ones? How about? Let me go up. I think it's right. How about unit box? Or just a rectangle box? How do you project onto a rectangle? God, I hope this is right. I had a weird feeling. But well, how do you project onto a rectangle? Yeah.
Take the max of that with.
Yeah, you saturate it, right? So you look at coordinate, you do it all separately. You take coordinate x3, it's got a lower, there's an L3 and a U3, and you set x3 is equal to x3 if it's between those two. Otherwise, if it's below L3, you set it to x3. If it's above U3, it's U3. So you saturate it, I guess. I hope that's right. Anyway, I think it's right. Okay, there's some other sets you can project onto easily. There's a bunch of them, and it's actually good to have in your mind a catalog. By the way, you can project onto a lot of sets. Depends on how much effort you want to put into it. How do you project onto a polyhedron? How would you project onto a polyhedron? I mean, it's not going to be an analytic solution, but how do you do it in general? A QP. So you solve a QP. You solve a quadratic program to project onto a polyhedron. So that's one. And we can talk about, so for example, there's some non-obvious projections. Ooh, we should put that on the homework. So project onto the unit simplex, for example, is a non-obvious one. That's not true. It's a homework problem. But anyway, I forget it periodically and then refigure it out and then swear that I'll remember it. And then I forget it and so on. Oh, anyway, okay, alternating projections. Okay, we'll look at an example. It's positive definite matrix completion. And let's see what that is. What happens is I have a symmetric matrix, and I have some entries are fixed, and I want to find values for the others so that I form a PSD matrix. Now, the truth is, if you were going to solve this problem, you'd really want to do something else. For example, you might want to complete the matrix in such a way that the determinant is maximized. That gives you a unique point. In fact, it gives you a beautiful point. It gives you a point when you complete a matrix in order to maximize its determinant. That's got all sorts of names. I guess in signal processing it's called, the Berg maximum something or other. In statistics it's got some name too. I forget what it's called. It's the maximum entropy completion or something like this. But you get a matrix whose inverse has zeros in the entries you can adjust. So I promise you that. That's just straight from the optimality conditions. But we're doing something simple. We're just doing feasibility. And so if you like, you could think of it this way. I'm going to give you some samples of a covariance matrix, and you are to fill in the other entries with merely numbers that are plausible. That's plausible means it's positive semi-definite. So, okay. So here's what we're going to do. The first projection is going to be onto the positive semi-definite cone. That's an easy projection. That you do. That's also a good thing to know, is you project onto the positive semi-definite cone a symmetric matrix by just truncating the eigenvalue. You just truncate negative eigenvalues. That's your projection. Okay? By the way, there's lots and lots of things like this, right? So, for example, how do you project a non-symmetric matrix onto the unit ball in spectral norm? That's the maximum singular value. So your set is the set of all matrices with maximum singular value or norm less than or equal to 1. Guess. I mean, if you know the answer, fine, but just go ahead and make a guess. How would you do that? I gave it away. Did you notice that? Yeah, you truncate the singular value. So you take the SVD of the matrix. If all the singular values are less than 1, you're done. You're in the ball. There's nothing to project. I mean, you don't have to do anything. You are projected. Otherwise, any singular value that's above 1, you replace it with 1. And you have a new matrix now. You have U sigma tilde V transpose. That's the projection. Okay? So anyway, projection is not it's a good thing to know, to keep in your mind what are the projections you can do cheaply and at what cost. It's a very good thing to know. Okay. Now projecting onto the set C2 is completely trivial. That's the set of symmetric matrices that have specified entries. How do you project onto that? You just simply take all the entries that are fixed and you reset them to the value they're supposed to have. Okay? So here's an example. It's a 50 by 50 matrix. So about half its entries are missing. So think of this as a covariance matrix, and I give you all of these entries, and you're to fill in the blanks you're going to fill in the blanks with just entries that are consistent and so on. So that's the picture. And by the way, the alternating projections algorithm is completely trivial. It calculates the singular value decomposition. It wipes out all the negative eigenvalues, reconstitutes the matrix. It's now positive semi-definite, but you messed up all the entries that were fixed. Now you go back and you fix all the entries that were fixed, but now you have a matrix that's not positive semi-definite, so you keep doing this. And the amount you correct each step goes down. By the way, you'll find this and related methods in statistics and machine learning. You'll find these things like this all the time in things like EM algorithm. You'll also find them in when you deal with missing data values is a very common. You'll see stuff like this where you alternate. You guess some numbers for the missing data, then you analyze. Then you go back and replace them, and then like that back and. So the interesting part is some, but I have to tell you, most of those problems, some of those problems are convex, most are not. So okay, okay. So here you get convergence is linear. It's not a big deal, but by the way, this means that we have not produced a positive semi-definite matrix. What it does mean is depending on whether you take an even or odd. If you take an even or odd iterate, the even ones have exactly the right numbers in the fixed positions, but it's got a tiny negative eigenvalue. The odd iterates are positive semi-definite, but the entries in the fixed positions are not quite what we asked them to be. Everybody see what I'm saying? And that's just because you're alternating back and forth. So if you wanted to project into it and have finite termination, you could over-project in the positive semi-definite cone, and you would do that by truncating eigenvalues that were smaller than you'd over-project. You wouldn't project onto the positive semi-definite cone. You'd project onto the cone where the eigenvalues are bigger than epsilon, and you could pick your favorite epsilon, like 1e minus 3. So you would eliminate positive eigenvalues. This would actually then terminate finitely, that method. That's your over-projection method. Okay. So we say a little bit about speeding up subgradient methods. So the truth is, I've said this many times, and you'll see it when you do this, these are basically really slow. I mean, I have to qualify that. They're really slow. They depend on the data, all sorts of things about them. By the way, that can be wrong. If it turns out if you're lucky for your problem class, if you're looking for 10% or 3% accuracy, these methods can work fine, just absolutely fine if you're lucky, especially with some kind of acceleration method. I'll talk about them in a second. You might ask, why would anyone use these? And we'll see soon, because there are going to be some methods that these things work with. For example, they generate completely distributed algorithms. We'll see that in a minute, which is very cool. Okay. But basically what happens is these things jitter around too much. And let me just draw a picture to show how that works. And there's very famous methods about this, long discussion of it. And the truth is I don't really fully understand it all. So in fact, this would be an outstanding project. Someone just, you have to have the right kind of slightly weird personality. But if you did, and you just decided, that's cool, I'll delve into this, I'll read all this. You don't have to read Russian, it's all been translated. So you could actually work out, because I don't actually know what best practices are for subgradient method. By the way, it is a topic of current, people are working on it now, coming up with new stuff, and it's really actually quite cool and interesting. So it's an absolutely current research topic. And if someone wanted to work on it, it'd be very cool. Okay, so let me show you the problem. Let's project onto two sets, this guy and this guy. And by the way, it kind of looks like this no matter what, because in the end game, in the intersection, this is the intersection. Did I do that right? Yeah, sure. Okay, let's say that's the intersection. Is that right? Yes, that's the intersection. Okay, there's the intersection. And you're here. Well, you go like this. You go like that, and then you go like that, and you go like this, and you get this thing, right? So, and in fact, you can see something now that all you need to do is take these things, and if you make them if you make them approach each other more and more close to tangent, the subgradient method just slows to like zip. It's got to work, but the point is it slows to something very slow. Now, when you see this, there's some kind of obvious things. I know this is kind of like, it doesn't really make any sense, but this tells you something here. It looks like a lot of other things too. It looks like the gradient method, I don't know if you remember that the gradient method does the same thing. It kind of goes in the wrong, it does this. And what's a suggestion here for how you might, what you might do, what you want to do? What's that?
You overshoot, wouldn't it speed up?
You could overshoot. Actually, I would say that there's a lot of things you could do. Overshoot would be one, but the main thing actually would be if you smoothed the subgradients. If you low pass filtered or smoothed the subgradients, you'd get the right direction. Because what happens is first you go this way, then you go that way. Then you go this way, that way. And what happens is this is just sort of like thermal noise. It's not really helping anything. You get a very small drift this way. So if you were to just smooth these things, you would do well. There are very fancy methods for this. There's a method called Dijkstra's algorithm. So it's Dijkstra's algorithm, not the Dijkstra of computer science. It's a different one. So there's multiple Dijkstra's algorithms, obviously. So there's a method here, and what it does is it looks at two, and then you really want to look at two of these, and then kind of go along that direction, because that's kind of where you want to go. So it's something like you want to go in the direction, you want to look at where you've been, you want to go back and forth one or two, and then go in that direction. By the way, this would work pretty well too. So the basic idea is you want to smooth things, and you can see this is one. This is called this is the heavy ball method. I guess that's direct translation from the Russian. I guess, but well, no, I know it. That's where it's from. And this says the following. I mean, it's really wild. It just says, yeah, go in the negative subgradient. But then this says, give yourself also a little bit of, I guess this is momentum, but in a heavily damped oil. And I think that's the correct model. And it says, sort of keep going the way you were going with a small factor, but then modify it this way. And I think that will do it here pretty well. It will smooth it down. That's one. Now there's all sorts of other methods. We're going to look at a whole other class of methods that uses subgradients but are faster. In fact, some of them are theoretically fast. Another one is this idea of conjugate directions. That's sort of what this is, where you make a two-term update, and these things are fast as well. Okay. But here's just to be specific about it, here's a couple. Here's one, is filtered subgradient. So this is what anyone in, I guess if you did signal processing or something like that, this is what you would do. What you'd do is you'd go in a direction S, but S wouldn't be just the last gradient. It would actually be a convex combination of the current gradient and the last direction. You can see this is actually not much different from the heavy ball method. It basically gives you a two-term recurrence. It just smooths. It gives you some smoothing like this. And this is one method. That's filtered subgradient. And then we poked around and found something that some Italians came up with, which was basically, again, they all have the same flavor. The current direction you'll go in is a linear combination or whatever, a positive linear combination of the current step size and the last direction. So and they give a very specific beta. It should be that. And gamma is some number in here. This thing is something in between 0 and 1.2, and they recommend 1.5, whatever that means. Yeah. So here's our PWL example again, and this is what happens if you here's the Polyak step length. This is just you use the current gradient, subgradient. This is the Italian step length here, I guess. And then this is if you just put in some smoothing or something. So these things get better, but not not radically. I mean, it depends. If you're looking for sort of 1% accuracy in your application, this could actually be very, very nice. And you will see soon there are many actual applications of subgradients, of subgradient methods. So actually being able to do subgradient methods efficiently would translate immediately to lots of things. For example, it's going to come up in flow control protocols and all sorts of stuff in networking and stuff like that. So, okay. See, is this going to work? No, that wasn't right. And let's see. And now we'll start the next one, which is constrained. Okay, so we'll now look at subgradient methods for constrained problems. And I'll stop. I'll just get a little bit into this, and we'll talk about it. Okay, so far we've just been talking about subgradient method for minimizing unconstrained minimization. By the way, unconstrained minimization, you can already do a fair amount with just that, because these things can be non-differentiable, so you can choose any. I mean, you can do all sorts of stuff. But it turns out the constrained is no big deal in this case. So the most famous method there is the projected subgradient method, and it looks like this. I mean, it's really simple. It goes like this. You do a subgradient update completely ignoring the constraints, and you project the result back down here. So, by the way, if you said in English projected subgradient, you would actually think of a different thing. You'd actually think of the projection applying to the gradient. Okay? That's not, so the English phrase projected subgradient method is, it's not the subgradient that's projected, it's the subgradient update that's projected. Okay? So, by the way, if the projection itself is linear, which happens if you're projecting onto a subspace or affine set, then they coincide. But otherwise, it's not. Okay? So, okay. So this is it. So I mean, it's really dumb if you want to optimize over positive variables, for example. Just minimize f of x over positive x. The algorithm is embarrassingly stupid. It looks like this. It's basically x minus equals 1 over k f dot get subgrad, period. Next line is pos project of x. That's it. And so you just remove its negative entries. It's just that simple. That's it. So these are very, very simple methods. So it just looks like that. But you can do more sophisticated ones, of course, too. Okay. So you get the same convergence results. This is described in the notes. And the key idea is this, is that each of the steps, the subgradient step and the projection, each of them, when you do the projection, you don't increase your distance to the optimal point. So, in fact, that's very important to know, because whenever when you have an algorithm and you have a proof of something that it works or whatever, basic rule of thumb is once you have a Lyapunov function that is, or a merit function or a certificate or whatever you want to call it, a potential function, that's another name for it. Once you have that, it says you can modify your algorithm in any way. You can do anything you like, as long as whatever you do doesn't increase that function. So if you have some heuristic method, you can apply it, you can interleave it, you can apply it at any step you like, but as long as you do not increase that function. Okay? So that's actually the practical use of having a merit function or a Lyapunov function or something like that, is that you can insert stuff and you can insert it with total safety in an algorithm. Okay? So in this case, it basically says the following. It says when you do that subgradient step, of course you get closer to x star because everything else is the same. When you project back onto the feasible set, you can't increase your distance. You actually move closer by projecting to every feasible point. Therefore, you move closer in particular to any optimal point. So that's how that works. I mean, you can actually work this out to see how this works. But let's look at some examples. So let's look at linear equality constraints. Here you want to minimize a function subject to ax equals b. Now projecting onto a solution of a linear equation, that's an affine set. That's easy to do. That's just z minus, and then that's the projection like that. And so you could write it this way. That's the projector here. And this is P of z. And do I have too many? I'm getting I'm getting that feeling of unbalanced parentheses here. But is that just from my angle? No. Okay. So it's quite disturbing from down here when you look up at this angle like this. It's less. Oh yeah. No. That's a mistake. Okay. So the projected update, subgradient update, is actually very simple. Oh, by the way, the projector now is actually it's actually affine. Okay, so for an affine function, they commute. If you have, in other words, the projector of alpha minus or x minus alpha g, you can apply it to the separate one separately. And if you work out, if I simply apply this projection to this thing, here's it's going to end up being this. So what you do is this. It's the same as taking x, taking the gradient, the subgradient, and projecting that onto the null space of A, and then stepping this way. So this is probably what people think of when they talk about a projected gradient or projected subgradient method. But it's only for equality constraints. So let me explain that. You're at a point that satisfies Ax equals B. You want to minimize f. So you need to take a step in some direction. Okay. Well, a safe step direction is anything in the null space of A, because that's going to preserve your Ax equals B. So this says find a subgradient ignoring that, and you project that subgradient onto the null space of A. That's this thing. And then that's now a feasible direction. So you might call this like a feasible subgradient direction. And this is the very specific one here. And just as a quick example, let's minimize the L1 norm subject to Ax equals B. Here you can work out what happens. It's quite straightforward. At each step you do a projection like this. You take the sign, because that's the projection of x is the sign here. And you simply, or that's a subgradient, I should say. If any of the x's are 0, then you just can take 0 if you like. It doesn't. You take actually your favorite number between -1 and 1, because it will make no difference. Any such thing as a subgradient. You project this onto the null space. That's this, and you do this. Now, by the way, this would be of really not much interest unless you had a problem where you can calculate this super fast. So, for example, if you're doing medical imaging or something like that, you've got 10 grad students and a whole lot and 90 papers and stuff like that behind some ultra fancy, multi-scale, multi-grid, PCG type method to solve some humongous least squares problem, because that's what this is. Then it says no problem, you'll just plug this in, and that's how you'll do it. This would be a bad choice, by the way, for something like that, but it doesn't matter. And here's how it works. And once again, we see that it is slow. So that's surprise, surprise, right? So that's okay. I mean, come on. What do you expect for an algorithm that is one line and whose proof is 2 lines? Okay, 3. I mean, come on. Something's got to give. Okay. We'll look at one more thing. Or maybe what I'll do is I'll quit here. This is actually, it's going to start getting very interesting, so we'll start there Thursday. But I want to make a few announcements, because a few people came in after we started. 2 important ones. We're actually going to, hopefully the registrar's email list will be up and running. Otherwise, we'll have to do it through Access. But please watch your email, because we're going to announce both a section and, believe it or not, a tape behind session. We're actually going to go ahead and retape lecture 1. Please come. You'll get extra credit or something like that, whatever that is. And the section is going to be just discussion of projects, just open, totally disorganized discussion of project. But it should be fun for everybody and useful. Okay, so we'll quit here.